Hey there kids, it's another snow day catch-up video. So today this video is going to be following your improper integrals one, and this is going to be talking about comparison tests in order to evaluate improper integrals. So I have a warm-up on a regular improper integral. Remember from yesterday, improper integrals are integrals approaching a horizontal asymptote like this one. Right, basically the end behavior going from 1 all the way out to infinity of 1 over x squared, or a vertical asymptote, where you're approaching maybe a vertical asymptote. If this had been a 1 to 0, or 0 to 1, you would be talking about the vertical asymptote at 0, or crossing over a vertical asymptote. For instance, if this integral had been negative 1 to 1. The graph of 1 over x squared, took Algebra 2 and I paid attention, looks like this. And since I'm talking about going from 1 to infinity, I am talking about collecting area here all the way out and wondering if the sum, if that sum, will converge to a value, or will it not converge. So quickly going through this one, remember we replace the improperness with a fake a, and then we're going to take the limit as a goes to that improperness. And integrating x to the negative 2 gave me negative x to the negative 1. Using the second part of the fundamental theorem. That's negative 1 over a minus negative 1 over 1. But putting in negative 1 over 1,000, negative 1 over 1,000,000, negative 1 over 1 bazillion approaches 0, and 0 plus 1 is 1. So this improper integral converges to 1. Here's another improper integral, very similar. Notice that all I've done is add 1 in the denominator, but this all of a sudden changes. This is like we did one like this yesterday, that it was a double improper, where this is inverse tangent. So again, replacing the improperness Fortunately, I took pre-cal and I paid attention, so I remember my inverse tangent graph, and that helps me. Because when I think about inverse tangent of larger and larger and larger values, I think about my graph of inverse tangent with its horizontal asymptotes at pi over 2 and negative pi over 2, which really I know because I know the tangent vertical asymptotes at negative pi over and pi over 2. So this becomes pi over 2 minus pi over 4, but of course that is 2 pi over 4 minus 1 pi over 4, which is pi over 4. So this improper integral converges to pi over 4. So both of these improper integrals that we're investigating horizontal asymptotes, what's happening as you take the integral off to the horizontal asymptote, worked out fairly nicely. So now for number 3, something to lead in what we're going to do today, I want you to think about the graph of 1 over x squared and the graph of 1 over x squared plus 1, or even the values. 1 over, as I go off to infinity, 1 over 1,000,000 squared compared to 1 over 1,000,000 squared and 1. 1 over 1 billion squared compared to 1 over a billion squared plus 1. As you get with this denominator here being smaller than this denominator, the ratio of 1 over a smaller denominator compared to 1 over a little bit bigger denominator, I hope that you can see that the graph of 1 over x squared plus 1 will always lie under the graph of as I go off to infinity anyway, 1 over x squared. That's going to be important to us. I mean, if x was 0, these two things would be equal, yes? Right, well, I guess you can't put 0. That won't be defined. But more importantly, as I'm going off to infinity, I want to make sure I can tell which function will always lie on top of the other one. That is nice. That's going to be nice to know for later on today. So let me refresh your memory about some things from pre-cal. The integrand here from pre-cal, that is an example of what we call a p-series function, 1 over x2 and exponent here. P-series you investigated as you went off to infinity and hopefully figured out that as long as this exponent is greater than 1 over x to the p, that p-series will converge. However, if you are less than 1, if your exponent is 1 or smaller, the p-series will diverge, and that's going to be, say, for the integral of the p-series. So, some basic improper integral rules where you don't actually, what's nice about, if you know these rules, you don't have to actually go through the anti-differentiation. Unless you are asked, what does the improper integral converge to, if it converges, then you have to integrate and find that number like we did in the warm-up of 1 or pi over 4. But sometimes you were just asked if the improper integral converges. And if you recognize these forms, you don't actually have to integrate. The improper integral, b being a number, a constant here, some constant off to infinity, horizontal asymptote, 1 over x to the p, that improper integral will converge as long as that exponent on x is greater than 1. If the exponent is 1 or smaller, the improper integral diverges. So again, I'm not saying here which value, if I converge, which value I converge to, but if I recognize this, I know I do have convergence as long as p is greater than 1. And if I'm asked for a value, well then I go find it. If my p is less than 1, diverges, right, diverges and go on. Notice that number 2 looks very similar, except that this time you're going from 0 to your constant here. This is a vertical asymptote issue, right? This is going off to the end. This is exploring what going off to your horizontal asymptote. This is the vertical asymptote issue, and you have the vertical asymptote at the end. So if you're sweeping, right, here's 0, 1 over x to the p over here. This will, as you start from some number b here, and kind of, you know, you're basically talking about going from an unbounded area over to here, this value will converge opposite here. If your exponent is less than 1, you will converge going towards the vertical asymptote and diverge otherwise. So be careful not to mix these two up, because they look similar, but it's all on whether you're approaching the vertical asymptote versus approaching a horizontal asymptote. This next one is not as common, but you will see it. This talks about your e to the function, so you know what that looks like. And this a number here, if this number is smaller than 0 or negative, for instance, maybe you have e to the negative 2x, or e to the negative x, or e to the negative 3x. Remember, those are really all 1 over e to the positive 2x, 1 over e to the x, 1 over e to the 3x, and as you remember from Algebra 2, those sweep off as you go off to infinity. So this, the e to the function, will always converge as long as you have your 1 over e to the, whereas if a is positive, if you remember that graph, shoots off, so therefore diverges. So, in the warm-up and in the problems you did yesterday, every time we were asked about converging or diverging, we actually integrated to find out, gee, did I get a value or did I get an infinity? The problem is sometimes I don't need to know what value an improper integral converges to. I just need to know if it does or does not. So if I have this integral, I can't integrate this. 1 over, by any means I know, I don't know how to integrate 1 over x to the 5th plus 1. Going back, I do recognize that I am dealing with an improper, and further, that it's investigating the horizontal asymptotic behavior off to the ends. So, if I want to know if, good night, Delaney, if this integral converges or diverges, I just want to answer that question. I'm going to compare it to a known improper integral. And the improper integrals that I know, boop, 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 those ones. I know my p-series and my e to those. So when I look over at this function here, I say to myself, 1 over x to the 5th plus 1 looks an awful lot like 1 over x to the 5th. Hey, p-series, help me out. A convenient p-series, and further I know this p-series converges because one over x to the 5th is a p-series of the form where p is greater than 1. Therefore, this p-series, this improper integral, converges. But I have to be sure and say that I know the convergent, the converging p-series has to be able to collapse on top of the unknown. And I want you to think of it, literally squishing. If you can reason and say that 1 over x to the 5th, again, because it has a smaller denominator than x to the 5th plus 1, x to the 5th plus 1 will always be a larger denominator than just x to the 5th. 1 over a smaller denominator compared to 1 over a larger denominator means that this ratio is bigger than this one as you go off to infinity. Graphically, here is 1 over x to the 5th. As long as I know that 1 over x to the 5th plus 1 behaves very, very much like this, but always will lie underneath of it, well, think of if this area, if this converges, then anything that lies underneath of it and behaves just like it will converge as well. So it's almost like I capture it, I drop down onto it. So since my p-series that behaves an awful lot like my unknown one converges, it not only behaves like 1 over x to the 5th plus 1, it is always bigger than or equal to 1 over x to the 5th, which converges on the given interval 1 to infinity. Therefore, I can say the unknown one converges to. I can't say what value. I don't know the value it converges to. Oh well, at least I know it converges. And for reasons that we will never get to, when I'm dealing with series and sequences, convergent series are the interesting ones. The divergent series, I would like to know if they're divergent because I'm going to get rid of them. It's convergent series that are applicable mostly to electrical engineering or just mathematical theory. So I might not know what value this improper integral converges to, but knowing it is convergent is useful. So here's my comparison theorem. No one is ever going to ask you about this word for word. This is the direct comparison theorem. If I assume that I have two functions such that I know that f of x, and for our purposes in the example I just did, that was 1 over x to the 5th plus 1, is smaller than something I knew, 1 over x to the 5th. And I know that I'm dealing with the improper integral of f of x. If I know the improper integral with g, which is the bigger guy, converges, then the one I don't know, but who looks think of it as cousins, who looks a lot like the one I know, then the integral of that function will always also be smaller than the integral of this one. And therefore, since this one converges by the direct comparison test, this one will converge as well. If the improper integral of f of x diverges, this is important. I'm going to change my ink color. Because if the improper integral of f of x, if f of x is the smaller one, and the smaller one diverges, then the bigger one that looks an awful lot, its cousins, looks an awful lot like its smaller cousin will diverge as well. So I'm going to go back up here and I'm going to draw both scenarios. Let's pretend this function, as I said before, let's pretend this one is 1 over x to the 5th. It's the p-series and I know it converges. Then 1 over x to the 5th plus 1, which lies underneath of it, that integral, right, will converge as well, because it's like 1 over x to the 5th collapses on it. However, if I switch that up and say that this is 1 over, let's say, x to the 1/2, which diverges, right? This diverges because p is less than 1. And if I have a function that is very similar to it, a cousin, and lies above it on the interval, since 1 over x to the 1/2 diverges, and it's smaller than its red cousin, the red one will diverge as well. So it's very important for the direct comparison test to know which situation you're dealing with. Which one is the small? Which one is the big? Which one of these is your known? If you know the small one, diverges, then the big cousin will diverge as well. But conversely, if you know the big one converges, then you know its smaller cousin will converge as well, because the big one will collapse on the small. Again, the other way, if you know the small one diverges, then it will sweep out divergently and sweep out the big one, and the big one will diverge as well. So, since you're not going to integrate, you have to write. Notice I don't have to do any calculus. I'm not going to integrate. I'm going to compare, which means I have to write for points. So I have to write. Since I know that 1 over x to the 5th from 1 to infinity converges, and I know that 1 over x to the 5th lies on top of 1 over x to the 5th plus 1. And, it's still not all, you have to tell me how you know 1 over x to the 5th converges, because it is a p-series with p greater than 1. So tell me what you know, how you know it, and the relationship between your known and your unknown. Since you're going to say converge, then the function you know has to be on top of the function you don't know, so that it can collapse upon it. And then you can make the conclusion that the improper integral 1 over x to the 5th plus 1 also converges. Notice there's no freaking calculus, really. I'm not integrating anything, so you do have to write all of this stuff out. Including that you have proven it by the direct comparison test. And yes, AP will understand if you say DCT for direct comparison test. So remember, this was the function and the improper integral that I knew. I know that converges because it's a p-series where p is greater than 1, and if you asked me to, I could do the limit as a approaches infinity and I could get a value. So converge to a number. But as soon as I make this 1 over x to the 5th plus 1, and I use the DCT, all I can say is I can't do any of this, and I won't get a value. I can use the DCT to conclude that 1 over x to the 5th plus 1 converges. That's it. We were not able to say what number our improper integral, x to the 5th plus 1, converged to. Just that it did converge, and by what test. So here's another example. Use the direct comparison test to determine if this improper. So notice again the word if. So I know that my answer is just going to be yes, it converges, or no, it doesn't. So I have to find a similar behaving p-series, because remember, of that list I had p-series rules and an e to the rule. So there's no e's in here. So I'm going to be thinking about p-series. I got a whole bunch of stuff going on here. Whoops, sorry. And one of the things I have going on is that my computer is freaking out again. I don't know why that happens. Sorry. Doody doody do. Love technology. There we go. Okay, so I'm going to do some fancy assumptions here. Firstly, here's my improperness going off to infinity, horizontal asymptote-ish, and behavior is what I'm asking for. And when I notice this, notice that the power of my numerator is x squared. The largest power in my denominator is x to the 4th. I don't technically have a rational function because of this issue, but think about the range. Hello, algebra, trig, algebra 2 and trig. The range of cosine x is between plus and minus 1, right? So as you go off into infinity and you have 1,000,000 to the 4th plus 2 times 1,000,000, all you're going to be doing here is adding one, at most 1 or negative 1. So whatever to you. You're out of my consideration. And now I am back down to kind of thinking about a rational function where I have an x squared here and an x to the 4th here. So if I reduce that, and again, if I 1,000,000 to the 4th plus 2 times only 1,000,000, you're not really that important either. So osmosis U out, then Hello, P-series. If I have an improper integral that converges to a value, well, 2 times that value will still be a convergent, will still be a number that I converge to. So that's why I can osmosis this 2 out and kind of forget about it. So 2 over x squared, 2 times the improper integral 1 over x squared. 1 over x squared does converge, right? Because it is a p-series where p is greater than 1. So my known one is greater than or equal to again, because this denominator here will always be, if you take x squared versus x to the 4th plus 2x plus cosine x, where this is only adding plus or minus 1, 1 over x squared, the one I know, is bigger than the smaller cousin, the one I don't know. Since 1 over x squared will always, that converges, and will always lie on top of the one I don't know, I can therefore conclude converges as well by the direct comparison test. So first I had to find a similarly behaving function. I had to say what I know about the similarly behaving function, how I know it. I have to show that since I'm concluding converging, that the function I know is bigger than the one I don't know and will collapse on top of it. Converging needs to collapse on top of the one that lies underneath of it, and then I can make this conclusion. I actually can integrate this with ln, so I can actually find, do the whole limit thing, but I'm going to pretend I don't. I say, hey, 1 over x plus 1 looks an awful lot like 1 over the x, where p is 1. Therefore, 1 over x diverges. But I've got a problem. This is the one I know, but I know it diverges. This one (1 over x plus 1) is in red. It lies underneath 1 over x. 1 over x diverges. It's not going to capture the red function. It's not going to collapse on top of it. So, inconclusive. I found a similarly behaving function. I know it diverges. If the one you know diverges, it needs to be smaller than the one you don't know. dagger. So I need a similar and smaller function because who I'm comparing it to diverges. So look at that. Now, you can also think of this as 1 over 2x, right? If I osmosis this back in, is 1 over 2x, or a half times 1 over x, going to lie under 1 over x plus 1? Start putting in numbers, right? So 1 over 2 times 100, so 1 over 200. Is 1 over 200 smaller than 1 over 101? Okay, tricky. But now notice, this is 1 over x, or 1 over 2x, excuse me, diverges. Notice that it will capture the purple function now. Because I know that f diverges, but f is under my purple function g, the divergence, which is a great book, by the way, movie to be coming out soon, will capture the purple g. Therefore, g diverges by dct. Once again, what do you know? How do you know it? What is the correct relationship? Since I know divergent, I have to get my function that I know is divergent under the unknown in order for me to use the direct comparison test and conclude that this 1 over x plus 1 diverges as well. So again, not a lot of math, but you got to therefore write all of this stuff. Sometimes the direct comparison test is a pain, and it's a pain mostly because I have to worry about, wait a second, which function is under, which function is on top. Do I have divergence? Then I need to be under. Do I have convergence? Then the one I know needs to be on top. Can sometimes make my brain spin. Well, there's a L'Hopital-ish kind of way around that. If I'm going off to infinity, so this doesn't work for vertical asymptotes, but if I'm going off to infinity, so investigating horizontal asymptotes, and I can show that the limits going to infinity of two similar functions, so once again I do have to find two functions that are cousins. If they both are behaving the same way as I go off to infinity, I can conclude that they both do the same thing. So if one converges, then the other one. If one diverges, the other one will diverge. So again, I still have to go back to my P series or my e to the series. Those are my handy-dandy ones that I just know. So I'm going to go back to this 1 over x plus 1. Remember when I tried to first use the direct comparison test with 1 over x, I couldn't do it. Right? And I was a little tricky and figured out how to do the 1 over 2x instead. Here we go again. I apologize. Let's see, what can I do while we're waiting? Should I sing? No. Recite poetry? No. Talk to you about life? Maybe. Did I tell you that if I wasn't a math teacher, I would have been a history teacher? Devin gives me crap for that all the time. It is true, I love history. And I almost did become a history teacher. I just decided that, if I don't like teaching, I don't know how much money I can make as a history major. Whereas as a math major, I could leave teaching and be a little bit more marketable. It all comes down to money now, doesn't it? All right. So, look at what I did. I found, remember, this is the function. This was the improper integral, the integrand of. This is what I know. This is its cousin that I know. And I made a ratio of them. It matters not which one you decide to make the numerator and denominator. I am just looking. I'm going to take the limit as x goes to infinity of both of these. And I want to see at the ends, do these functions behave enough alike? I did some algebra, right? I just took this division. 1 over x divided by 1 over x plus 1 is the same as 1 over x times x plus 1 over 1, right? That's how I got x plus 1 over x. Oh, there's my phone. And I say, well, what happens as you go off to infinity of x plus 1 over x? Right? Technically, you get infinity over infinity, so you L'Hopital that. There he is. And I take, remember L'Hopital says take the derivative of the numerator and the derivative of the denominator. And I get 1. So, two similarly behaving functions, one of which I know, 1 over x, is a p-series with p equal to 1 and diverges. Since I showed with a limit comparison test that these two functions, as you go off to infinity, behave very similarly because I got a ratio of 1, they are going towards infinity at the same rate. That allows me to say that since the improper integral 1 over x diverges because it is a p-series and p is equal to 1, and the limit that I got was a number, 1. And again, it doesn't matter what this number is, as long as you get a value that is neither 0 nor infinity. This value, this numerical value, says that these two functions behave very similar at the end. And since you know this one diverges, then this one does too. I didn't use the direct comparison test though. I used the limit comparison test. And yes, just like DCT, you can call this the LCT. Be careful. The limit comparison test is only valid if you actually get a value for the limit, and that value cannot be 0. If you get 0 or infinity, what that says is your two functions that you chose and you related don't behave enough alike at the end to be able to make a conclusion. But if you get a number, I don't care if it's 1, 2, 7, 14, I don't care what that number is, as long as it is a number that is not 0 nor an infinity, you can use the limit comparison test to make the conclusion. If you get 0 or infinity, the LCT is inconclusive and you have to go back to trying direct comparison test or some other method that we don't know yet. Okay. So, your homework is going to be a handout that we will have available on Edline or have some copies of for you. But when you are doing the homework for comparison tests, the first thing you have to do realize that you have an improper integral, and that you are only asked if you converge or diverge. Okay. So that's how I know. I'm not asked to, the other directions were find the value to which the improper integral converges or state that it diverges. Those directions are different from the directions that will be on this handout, which are just saying, does the integral converge or diverge? So I'm looking for the word if, and that's how I need to use a comparison test. You have two comparison tests. You have the DCT and you have the LCT. For both of these, the requirement for both of them is that you find a similar known function. And the ones that you know P series or e to the. Then you must state what you know, and what you know is it converges or diverges. state how you know it. Your P series, P greater than 1 or P less than 1 for diverging, your e to the ax, where a is less than 1, or for converging, a greater than 1 for diverging. If you're doing the DCT, then you must state the relationship. In other words, who's bigger, who's smaller, and make sure it's appropriate for whether you're showing convergent or divergent. If you're doing the LCT, again, this order, numerator and denominator, really doesn't matter. Known to unknown or unknown to known, it doesn't matter. You may at some point have to L'Hopital. To evaluate the limit, and remember your limit has to be something between 0 and infinity in order to conclude converge or diverge, and then by the appropriate test. So that's it for comparison tests. We're going to be using, while we're using this for improper integrals now, this is going to come back again towards the end of this unit after we get done investigating our numerical and power series and talk about whether series converge or diverge. Something to look forward to. See you then. Bye.